Today I'm going to be covering the first chapter of NCRT 9th Standard Math, which is called Number Systems. Now in number systems, we're going to be covering the definition of different types of real numbers, as well as certain operations between those real numbers and types of real numbers that the student may or may not already know. Now, the first type of real number, the smallest subset, which is still infinite, is called a natural number. Natural numbers, they start from 1, and then these are the traditional numbers used in counting. These are numbers that naturally occur. So if there's a defined amount of a substance, right, that's in defined pieces, then you can count them as 1, 2, 3, and it goes on infinitely, right? Natural numbers is the smallest subset that we're going to study here of different types of real numbers. Now, there's another type of real number, which includes all natural numbers but one more number. That means it starts from 0. And this is the whole numbers. You see, 0 is argued to be a not natural number for a long time, and many mathematicians didn't want to accept it as a number at all, but it turns out they just had a very stiff definition of number. So 0 is a whole number. Whole number is simply defined as it is whole, right? It is an amount that exists, and the numbers themselves, the individual numbers themselves, are not broken up into pieces and added on. For example, in the number 2.5, right, there's a 0.5, there's another piece of quantity that's broken into 2 and then added on. Okay, whole numbers are perfectly quantized. And whole numbers also go on infinitely. Infinite just means it'll never run out. It doesn't mean it's the biggest or smallest set, right? Because there's an even bigger set. This is called integers. Integers include all whole numbers. So 0 is in the middle, right? They include all the natural numbers, and they include all the negative natural numbers. Now, the way integer was defined is as what you can count, right? Numbers that are normally used when counting, which don't have a decimal point, right? They don't have any value beyond their decimal point. These are what you call integers. There's yet another bigger subset that's even bigger than integers, and this is called rational numbers. Rational comes from the word ratio, right? Any number that can be expressed, let me just write this. Here's a rational number. And a rational number can be expressed as P by Q, and Q is not equal to 0. And the reason Q is not equal to 0 is because division by 0 is actually impossible. Now here, since we have the definition of a rational number, we can see that all integers are rational numbers, and all whole numbers are integers, and all natural numbers are whole numbers, right? P by Q, where Q is not equal to 0. So any number that can be expressed as a fraction of two natural numbers is a rational number. So this is once again a point where the definition of a natural number comes in, because frankly speaking, okay, sorry, 2. Yeah, it can be negative natural numbers as well, right? Yes, that is right. Negative numbers also count as rational numbers, so P or Q can also be negative, right? But it still has to be either a positive natural number or the negative version of that natural number for the ratio P and Q, and if it can be expressed as a ratio, it's a rational number. Now, how do we know? By looking at a number, because we know how to figure out if a number is natural, whole, an integer, etc. How do we figure out by looking at a number that it is rational, right? First of all, what kind of numbers might be rational? The kind of numbers that might be rational include, of course, integers. That's one. They also include fractions, And then let's get on to decimal points, right? Decimal numbers such as 1.5, 1.51. These two are both rational numbers. The reason is that their decimals do not extend forever. Other types of decimal numbers that include 2.9, 2.8, but really 9 and extends forever, 8 and also extends forever. These ones are also rational numbers. You can also figure out how to express these as in the form of P by Q, where Q is not equal to 0, right? Repeating but continuous decimals, but they still have a repeating pattern. These two are considered rational numbers, right? For something to be an irrational number, that means when you try to express it in the standard base 10 form as a number, right? It turns out not just a decimal, but you cannot find, it first of all goes forever, and there's no repeating pattern no matter how long it goes, right? This is how you know that a number may be irrational, okay? So non-repeating continuous decimal numbers are always irrational. That said, there are ways to prove a number might be non-repeating or not, and I'm quite sure that it's too advanced for 9 standard. So I just told you that these numbers here, 2.999, 2.888, since they're repeating decimals, these are definitely rational numbers. How do we actually make it shown that these are rational numbers that can be expressed as P by Q? Well, I'm going to show you right here. Let's take number 2.9 continuous to infinity, right? It turns out that 2.9 into 10, let's take this as A. So of course 10A minus A is equal to 9A. Great. 10A therefore is 29.9 infinity minus, and then A is therefore 2.9 over to infinity, right? This infinite row of 9s, they both are equal here and they cancel. 29 minus 2 is equal to 27, right? So this is 10A, and then A, 10A minus A, which is equal to, right, implies in fact that 9A is equal to 27, implies in fact A is equal to 3. Why exactly would 2.99 up to infinity be equal to 3? Intuitively you can tell. But if you still want to deny that 2.9 all the way to infinity is equal to 3, I'm going to try this again with 2.8 to infinity, right? It's really important to actually show this. I really think this is important. Now, this, of course, I haven't actually found this in NCRT. I learned it from ICSE. But I do believe it's important to see how you can prove that a continuous decimal is, in fact, a rational number. So then, 10 times of this, 28.8 there, minus 2.8 there. 8 and 8 cancel, right? That is equal to 26. And therefore, 9 of B is equal to 26, because let's say that 2.8 continuous is B, right? This implies that B is equal to 26 by 9 right here. So I can prove that this continuous decimal 2 is also equal to a fraction, P by Q, where neither P nor Q are equal to 0. Now, of course, P and Q, right? P and Q, where neither P nor, where Q is definitely not equal to 0. P actually can be equal to 0, to be honest, and it can still be irrational. But yes, Q cannot be equal to 0, right? Now, here's the thing. B is equal to 26 by 9. It's also equal to 260 by 90. 260 by 90, therefore, is called an equivalent rational number. The smallest form is 26 by 9, because 26 by 9 are co-prime numbers. They have no common factors other than 1, right? So, yes, of course, every equivalent rational number can be simplified to p by q, where p and q are not just q not being 0, but p and q are co-prime. That's the first thing, the first operation with rational numbers that I want to show you. Now, irrational numbers. What exactly is an irrational number? Well, an irrational number is one that, when it is expressed in a decimal, ends up being a never-ending, non-repeating decimal, right? Things such as root over 2, root over 5, and pi, these have all been found to be non-repeating, never-ending decimals. So therefore, you cannot use that operation that I showed you to multiply it by one thing here, by a multiple of 10 at the top, and subtract itself from the bottom, and actually get a fraction. You cannot do this, right? Now, the type of irrational number that we can still work with very easily and do some more operations with, these are the square roots of prime numbers. The square root of a prime number is always irrational. That's the first thing. And as a matter of fact, even 2 into root 2 is also irrational, right? Because as long as this is a square root of something that is not a square itself, it's going to be irrational anyway. Okay? Now there is another operation that you learned in this chapter, is how to actually geometrically derive the value of irrational numbers that are in the form of the square root of a prime number. You see, to derive the value geometrically of an irrational number that is the square root of a prime number, well, let's draw a number line. Right? Here's a number line. We know, for example, Pythagoras' theorem. What is that? Root over a squared plus b squared is our hypotenuse line. Then all it seems we have to do is draw something where the hypotenuse is going to be root over whatever we want. If we want the square root of 3, then all we need to do is 1, 2, base is 2, root over a squared plus b squared. A squared therefore has to be a squared has to be 2 and b squared has to be 1, which means a has to be root 2. So to get root 3, we need to first find root 2. So yes, first find root 2. Okay, to get root 2, horizontally it's 1, vertically also its height has to be 1, right? And of course, this here is going to be root over 1 plus 1, or 1 squared plus 1 squared, which is in fact equal to root 2, right? So this here is root 2, we can get our compass and we can just dot it down, right? Here is going to be root 2, right? Then for square root of 3, root over root 2 squared plus 1 squared. That is square root of 3. That is what square root of 3 is equal to. So we have our root 2 here, and then it has to be 1 high again, right? Right to here, and then here. Use our compass. We can find that the root of 3 is still between 1 and 2, but it's closer to 2. This is a way that you can geometrically find the values of the square root of prime numbers. You just have to have a slightly smart application of Pythagoras' theorem. So those are the first two, right? Another operation that is taught in this chapter is operations between square roots and exponents of natural numbers. Right? Because the square root of a negative number is not actually possible. There is no square root for a negative number. Right? So, what sort of operations can we do? Well, if 2 to the power m was 2 to the power n. We can't do any operations. But if it's 2 to the power m into 2 to the power n, this we know is equal, this I'll tell you is equal to 2 to the power m plus n. That's the first operation we can do, right? 2 to the power m minus 2 to the power n equal, we can't simplify this further, but 2 to the power m divided by 2 to the power n is equal to 2 to the power m minus n, right? These two here, these are simplification operations that we can do on exponents. This also is going to be taught in this chapter. What else is actually taught in this chapter? Yes, proving that repeating, but okay. Fine. Okay. How many minutes was that?
Okay, say you just conclude. We'll continue on next chapter.
Okay, anyway, there are a few more topics that are taught in this chapter, but for now the video is extending too long.